Have you ever looked up at the night sky? Have you ever marveled at the sheer scale of the universe? It is a vast and mysterious place. Billions of stars are scattered across galaxies. These galaxies themselves are clustered together in immense cosmic webs. Our understanding of this grand stage is built on incredible scientific achievements. We have theories that can describe the graceful dance of planets and detail the fiery hearts of stars. Yet deep within this understanding lies a profound and tantalizing puzzle. The first is Albert Einstein's theory of general relativity. Published over a century ago, it remains our best description of gravity. General relativity paints a beautiful picture of the universe. It tells us that space and time are woven together into a single dynamic fabric called spacetime. The second pillar of modern physics is quantum mechanics. This theory describes the universe at the other end of the scale, the world of atoms and subatomic particles. It is a world that is fuzzy, uncertain, and probabilistic. Unlike the smooth, predictable universe of general relativity, the quantum world is bizarre. Herein lies the problem. We have two magnificent theories. Separately, they are perfect, but they are built on completely different principles. Both theories should apply, but when we try to use them together, the mathematics falls apart. Think about the center of a black hole. Here, an enormous amount of mass is crushed into an infinitesimally small point. This is a situation where immense gravity operates on a tiny subatomic scale. We need a theory of quantum gravity. Before Einstein, we had Isaac Newton's law of universal gravitation. Newton imagined gravity as a mysterious force, an invisible rope pulling objects towards each other. Einstein offered a revolutionary new perspective. He suggested that gravity is not a force at all. Instead, it is a consequence of the geometry of the universe itself. It means that objects in orbit are not being pulled by an invisible force. They are simply following the straightest possible path through the curved spacetime created by the sun's mass. General relativity is the ultimate theory of the macrocosm. It describes the universe on the grandest scales with breathtaking elegance and accuracy. Now let us shrink ourselves down, far smaller than any planet or star, beyond the scale of everyday objects and into the realm of the atom. Here, the elegant and deterministic rules of general relativity no longer apply. We have entered a different world, governed by the laws of quantum mechanics. The quantum world is fundamentally a world of probability and uncertainty. Particles can be in multiple places at once. They can tunnel through barriers that should be impenetrable. Despite its strangeness, quantum mechanics is fantastically successful. It is the foundation for much of our modern technology. The fundamental nature of reality described by these two theories could not be more different. One is a sweeping classical symphony. The other is a chaotic improvisational jazz performance. The issue is that we know the universe is a single, unified entity. It cannot operate according to two contradictory sets of rules. The apple that falls from the tree is governed by gravity, but that apple is made of atoms, which are governed by quantum mechanics. The universe does not care about our neat separation of scales. It seamlessly integrates the large and the small. There are specific places in the universe where this clash of titans becomes a real physical problem. The most famous example is the heart of a black hole. The equations produce infinities, which is a clear signal to physicists that the theory is wrong. It is a signpost pointing towards a deeper, more fundamental theory. The same problem occurs when we try to describe the very beginning of the universe. In the first fraction of a second after the Big Bang, the entire observable universe was smaller than an atom. To understand how the universe began, we need a theory that can handle both quantum effects and strong gravity simultaneously. We need a theory of quantum gravity. Beyond the problem of singularities, black holes present another profound puzzle. This puzzle is known as the black hole information paradox, stemming from a discovery made by Stephen Hawking. He discovered that black holes are not entirely black. They should glow faintly, emitting a trickle of radiation over immense periods. Here is the paradox. One of the most fundamental rules of quantum mechanics is that information can never be destroyed. So, what happens to the information about all the things that fell into the black hole? This creates a fundamental conflict. Both principles cannot be correct as they stand. This paradox is a stark illustration of the deep incompatibility between our two best theories of nature. The need for quantum gravity is not just confined to black holes. It's essential for understanding our own origins, the key to unlocking the secrets of the very first moments of the universe. According to our current cosmic model, the universe began with the Big Bang around 13.8 billion years ago. We can see the afterglow of this event in the cosmic microwave background radiation. In the first tiny fraction of a second, the universe was a maelstrom of energy, crushed into a volume smaller than an atom. The temperature and density were beyond anything we can comprehend. In this primordial furnace, the universe was both unimaginably massive and infinitesimally small. This is the ultimate domain of quantum gravity. Perhaps the most profound reason we need a theory of quantum gravity is to answer a very fundamental question: what is the nature of space and time? General relativity treats spacetime as a smooth, continuous fabric. Quantum mechanics suggests that everything in nature is quantized. So, it's natural to ask, is spacetime itself quantized? Many physicists believe that if we could zoom into the Planck scale, we'd see that spacetime's smooth appearance gives way to a grainy, pixelated structure, perhaps like a digital image is made of pixels. Time might not flow continuously, but instead tick forward in incredibly small, discrete steps. This lumpiness is a defining feature of the subatomic realm. Ultimately, the quest for quantum gravity is a search for a more profound and unified description of reality. It's driven by this deep-seated belief among physicists that the universe shouldn't be governed by two contradictory sets of laws. The elegance and simplicity of physical laws suggest that there should be a single underlying framework that explains everything. This desire for unification has been a powerful engine of scientific progress for centuries. A successful theory would likely reveal a deeper connection between the fundamental components of our universe: space, time, matter, and energy. It might show that they're all different manifestations of a single underlying entity. Some theories suggest that spacetime itself isn't fundamental, but instead emerges from a more basic network of quantum information, kind of like a hologram projected from a lower dimensional surface. So, how are physicists trying to build this grand, unified theory? One of the most famous approaches is known as string theory. It's an idea of breathtaking ambition and mathematical elegance. String theory proposes a radical departure from how we view fundamental constituents of matter. For centuries, we've thought of particles as tiny, zero-dimensional points. But string theory suggests this is an oversimplification. It postulates that all particles are minuscule, one-dimensional loops of vibrating energy. Just as a violin string can vibrate at different frequencies to produce different musical notes, these fundamental strings can vibrate in different patterns. Each unique vibrational pattern corresponds to a different particle. In this view, the entire particle zoo is nothing more than different notes of a single cosmic symphony, played on these tiny, fundamental strings. What is truly remarkable is that when physicists explored the mathematics, they found something they weren't initially looking for. Among the vibrational patterns, one emerged that had precisely the properties of the graviton, the hypothetical quantum particle of gravity. However, this elegance comes at a price. For the mathematics to work consistently, the universe must have more dimensions than the 3 of space and 1 of time that we experience. Most versions require 10 or even 11 space-time dimensions. While string theory has long been dominant, it's by no means the only approach. A major rival, which starts from a completely different philosophical standpoint, is called loop quantum gravity, or LQG, whereas string theory begins with quantum mechanics and finds gravity emerges. Loop quantum gravity starts with Einstein's general relativity. It takes Einstein's dynamic geometric spacetime seriously and tries to apply quantum mechanics directly to the fabric of space and time itself. The core idea is that spacetime is not the smooth, continuous sheet that Einstein envisioned. Instead, if you could zoom in to the Planck scale, you would find that space is built from discrete chunks. It has a granular atomic structure. LQG describes this structure as a network of interconnected loops, forming a web of abstract links and nodes. This network is called a spin network. Each loop carries a quantum of area, and the nodes carry a quantum of volume. In this picture, space is not an empty stage where things happen. Space is the things that are happening. The spin network is reality. Particles aren't separate entities moving through this network. They're perhaps specific tangles or braids within the network itself. One appealing feature is that it naturally avoids singularities. Because space is made of indivisible units, you can never crush matter down to zero size. There is a smallest possible volume, providing a mechanism for the big bounce idea of cosmology. The quest to unite gravity and the quantum world is like climbing a great mist-shrouded mountain. String theory and loop quantum gravity represent two main paths, but they're not the only ones. Physicists, not certain which path will lead to the peak, are exploring several other intriguing and creative ideas. These alternative theories often take different starting assumptions and can lead to radically different pictures of fundamental reality. One alternative is causal set theory. This approach takes discreteness even more seriously. It proposes that the most fundamental thing in the universe is a collection of discrete space-time events. Everything else emerges from the relationships between these events. The only truly fundamental structure is the order in which these events occur, the network of cause and effect. It's a minimalist approach, trying to build the universe from the simplest possible ingredients. Another fascinating area is asymptotic safety. This theory takes a more conservative approach. It wonders if we really need a radical new theory at all. Maybe the problem isn't with general relativity or quantum mechanics, but with how we are trying to combine them. Then there are even more speculative ideas like emergent gravity. This proposes that gravity is not fundamental at all, but emerges from the collective behavior of more fundamental, microscopic constituents, much like thermodynamics, emerges from the statistical mechanics of atoms. With so many different approaches, it's natural to wonder which one is correct. Is it a competition where one theory will triumph and others discarded? There's another, more tantalizing possibility. Maybe these different theories are not competing paths, but different views of the same underlying reality. It's possible that string theory, loop quantum gravity, and other approaches are all capturing different aspects of a single, deeper theory that we just haven't fully grasped yet. They might be different mathematical languages describing the same fundamental physics. Intriguing hints of this possibility already exist. For example, the holographic principle within string theory suggests that a theory of gravity in certain dimensions can be equivalent to a quantum particle theory without gravity in one fewer dimension. Some researchers are even working to see if loop quantum gravity could be described by such a holographic principle, which would build a bridge between the two leading theories. Ultimately, the final theory might be a grand synthesis. It could be a new framework that incorporates the best ideas from all the current contenders. It might involve vibrating strings, granular spacetime, and emergent properties suggested by other approaches. The journey towards this unified picture is one of the most exciting intellectual adventures in science. It's a collaborative effort, with thousands of physicists around the world contributing pieces to this monumental puzzle. Despite all the brilliant ideas and elegant mathematics, the entire field of quantum gravity faces a colossal obstacle. This is the single greatest challenge of all, a profound lack of experimental data. Science progresses through constant interplay between theory and experiment. In the search for quantum gravity, though, this loop is almost completely broken. The problem is one of energy and scale. Quantum gravity effects become significant only at the Planck scale, a realm of unimaginably high energies and incredibly tiny distances. The energy required to probe this scale directly is about a quadrillion times greater than what our most powerful particle accelerator can achieve. Building an accelerator capable of reaching these energies might need to be the size of our entire solar system. Without direct experimental access, physicists are left in a difficult position. They're like cartographers trying to map a distant continent with only the faintest glimpses of its shoreline. They're navigating a vast theoretical ocean without a compass. This is why physicists are so creative in their search for indirect evidence. They're looking for tiny residual effects of quantum gravity that might be detectable in our low-energy world. The second major challenge is just the sheer mathematical complexity of the theories themselves. The mathematics required to even begin to describe quantum gravity is at the absolute forefront of human knowledge. Developing these theories isn't just a matter of having a clever idea, It requires inventing entirely new branches of mathematics just to even write down the equations. This makes progress incredibly slow and painstaking. For string theory, the mathematics involves complex geometry in higher dimensions, sophisticated concepts from supersymmetry, and incredibly intricate calculations. The theory is not yet fully formulated. What we have is a collection of different versions that appear consistent, but we lack the single overarching equation from which everything else could be derived. It's like having several complete chapters of a book, but no understanding of the full plot. Loop quantum gravity faces its own mathematical hurdles. The theory is built on spin networks, which are abstract mathematical graphs. While this provides a compelling picture of quantist space, it has struggled to describe the nature of time. This mathematical labyrinth means that even if we had experimental data, we might not be able to use it. For both theories, performing calculations to get precise numbers for real-world experiments is often forbiddingly hard or impossible. Beyond experimental and mathematical challenges, string theory faces a deep conceptual problem that has caused much debate: the landscape problem. The mathematics does not specify a unique way for extra dimensions to be curled up. Instead, it allows for a staggering number of different possibilities, each with its own shape and structure. Estimates suggest there could be at least 10 to the power of 500 different ways to compactify the extra dimensions. Each solution would result in a different universe, with its own distinct set of physical laws, fundamental constants, and collection of particles and forces. This vast collection is what physicists call the string theory landscape. Our universe, with its specific life-friendly laws, would be just one tiny island in an unimaginably vast cosmic archipelago of other possibilities. This creates a serious issue for predictive power. If string theory can describe almost any universe imaginable, how can it make a definitive prediction for our own? A theory that predicts everything, in a sense, predicts nothing at all. This has led to controversial ideas like the anthropic principle. This suggests that we find ourselves in our particular universe for the simple reason that we could not exist in any of the others. While this might be true, it is deeply unsatisfying for many physicists. As we stand today, on the precipice of a new era in physics, the path towards quantum gravity remains shrouded in mist. The challenges are monumental, perhaps the greatest intellectual hurdles our species has ever faced. We are grappling with technological limitations that cannot yet probe the Planck scale, and wrestling with mathematical frameworks of such complexity that they push the boundaries of human thought. Yet, despite these formidable obstacles, there is an undeniable sense of optimism. The future will be built upon a delicate partnership between theoretical insight and observational ingenuity. While we may not be able to build a solar system-sized particle accelerator, our ability to observe the cosmos with ever-increasing precision is growing at an astonishing rate. New telescopes are opening new windows onto the universe. Cosmology will be a key battleground. The cosmic microwave background holds a treasure trove of information about the universe's first moments. Scientists are meticulously scanning this ancient light for subtle patterns that could betray quantum gravitational effects. Ultimately, the breakthrough may come from a slow convergence of evidence from multiple independent lines of inquiry. A hint from gravitational waves, combined with a particle physics anomaly and a strange cosmic pattern, could all point towards a single, coherent picture. Beyond the technical details, the quest for quantum gravity resonates with something deep within the human spirit. It is a reflection of our innate curiosity, the same drive that led our ancestors to look up at the stars and wonder what they are. This is not just another scientific problem to be solved. It is an engagement with the most fundamental questions we can ask about our existence. What is space? What is time? From what did the universe emerge? The physicists working on quantum gravity are explorers in the truest sense. They are venturing into territories where no human mind has gone before, navigating with the abstract tools of mathematics and the faint light of physical principles. The thrill lies in the unknown, in the possibility that the answer will be something more strange, more beautiful, and more elegant than anything we have yet imagined. It is a journey fueled by the pure, unadulterated joy of discovery and understanding. This quest also represents the pinnacle of human collaboration. It is a global effort, transcending national borders and cultural divides. Thousands of brilliant minds are contributing their unique perspectives and skills to this grand project. It is a testament to what humanity can achieve when it focuses its intellectual energy on a shared goal of expanding knowledge for its own sake. To follow the story of quantum gravity is to watch science happening at its most ambitious and most profound. Should the quest for quantum gravity succeed, the consequences will extend far beyond physics. It will not simply fill a gap in our equations. It will fundamentally reshape our conception of reality itself. A successful theory would likely force us to abandon deeply ingrained intuitions. Our familiar notions of smooth space and universally flowing time may be revealed as mere illusions, emergent properties of a much deeper, stranger reality. This new understanding would trigger a philosophical revolution. It would provide a new foundation for thinking about our place in the universe. If space-time itself is emergent, what does that say about the nature of existence? A theory of quantum gravity would become a new lens through which we view the world, influencing art, philosophy, and our collective human culture for generations to come, much as the discoveries of Copernicus and Darwin did in their time. We are on the verge of potentially rewriting the first chapter of the cosmic story, replacing the placeholder of the singularity with a coherent physical description of our own genesis. We may finally understand the true nature of black holes. The search for quantum gravity is, in the end, a search for ourselves. It is an attempt to read the ultimate instruction manual of the cosmos that has given rise to us. It is a journey to understand the fundamental grammar of the physical world, the rules that govern every atom in our bodies and every star in the sky. While the path is fraught with difficulty, the potential reward is the most complete understanding of the universe that humanity has ever possessed. It is the final piece of the puzzle, the key to a unified vision of reality that will stand as one of the greatest triumphs of the human intellect.